Okay, so let us continue our discussion of regression. We got this equation for our in-sample error, and this is the linear algebraic form. If you remember from like our knowledge of algebra, if we have an equation of the form ax squared plus bx plus c, and we differentiate it with respect to x, we'll get something of this form, 2ax plus b. And so there is like a similarity in the kind of values we have in this equation. For example, this one has the squared term, and then this has a single variable value just like bx here, and this is like the constant term just like the c in our equation. So because there is this equivalence between an equation of this form and the E in that we just derived, we can directly write the gradient of E in as 1 over n. And by the way, this is left to like for the students to use vector calculus to verify whether this is correct or not. But this is like the intuition behind getting this result when we calculate the gradient of E in with respect to W, right? So what we're going to get is 2 times x transpose x W minus 2 times x, because the 2 is already there, right? So 2 times x transpose y. And then we have to set it equal to 0 to get the minimum weights, right? So these are also known as normal equations. So this is also known as the normal equation. And when we set it equal to 0, we set this thing equal to 0, what we get is x transpose xw equals x transpose y, right? And together these are known as normal equations in linear algebra. And now we are interested in finding the optimal W for this, right? And so if this term here, if and when, rather when this is invertible, we can multiply both sides by its inverse, right? So if we multiply both sides by the inverse of this term here, what we get is, and this is known as W linear or LIN, equals X transpose X inverse times X transpose Y, where X transpose X is invertible. Now, in many cases, this might not be the case. So when X transpose X is not invertible, in the most like general scenario, let's say it's not invertible, then we have to get something that's known as the pseudo inverse of this, right? So what we need to get is the pseudo inverse of this term here. Okay, that's a very technical sort of side to finding the inverse, and so we're not getting into that. All we know is that we can get the pseudo inverse instead of the actual inverse, and then substitute that still to get this WLIN. So eventually for regression, we have an exact formula to get the optimal weight, and that exact formula is given by this, right? So we have produced this exact formula, and we can call this overall this process, although we derived like the gradient of E in this lecture, but we know that we can do it, and so like eventually we will come up with something that looks like this. And so we have this like one-step pseudo-inverse algorithm. This entire thing is known as the and basically getting this WLIN, we already have the formula. So if you just substitute the values and get this value is known as the pseudo-inverse algorithm. I'm going to summarize this as well. So this is known as the pseudo-inverse algorithm, and it's just like a one-step algorithm if you think about it. As opposed to this algorithm, right? It just like brings up one solution in a single step. It doesn't seem like learning, but actually it is learning, because what we are doing is we are using some theoretical basis and we are producing this final hypothesis. So essentially this Win is nothing but the G that we've been after is what we are producing here. So as long as it does well on a new point, we have learned, right? So we have arrived at this formula for WLIN, and that is going to define my hyperplane, or that is going to define my line. And as long as that line does well, it predicts well for a new point, I have my G, right? So I have learned. Okay, so having said that, this is my pseudo-inverse algorithm. Let us summarize the pseudo-inverse algorithm. How do you apply it to an actual problem? So summarize pseudo-inverse algorithm. Okay, what is step 1? Step 1 is put your data in matrix form. So put your data in matrix form, which means, what does this mean? So basically, this is my y, so all the y values that I have, y1, y2, and so on up to yn, right? And x, if you remember the x1 transpose, x2 transpose, and remember this is the augmented like vectors, xn transpose. Okay, so that's like getting your data ready. Second, apply pseudo-inverse algorithm. That's it. That's all you have to do. So what does that mean? Basically, apply this formula here that we derived, WLIN equals X transpose X inverse X transpose Y, right? This is the equation that we came up with, or more precisely, like this is written as, for like the most general scenario, this is written as X pseudo inverse Y, where X pseudo inverse is nothing but X transpose X and X transpose. So basically when my inverse for this exists. If not, then we have certain algorithms to get some kind of an approximation for that. But that's it. That's it. So in this step, we have learned. That's all that we need for learning. So that's it. So basically in step 3, you have come up with your final hypothesis, G of X, which is nothing but WLIN transpose X. That's it, like in one step. So now here all I'm doing is, my goal is to actually get some GXI and see if it gives me like the YI that I have. So just like the actual value matching is happening here, as opposed to a classification problem where we were looking at the sign, right? So this algorithm gives you the exact optimal in sample error, because that's what we did when we calculated the gradient and set it equal to 0. Okay, so having said that, what happens to the first step of learning that we've been talking about? What happens to that first step of learning in regression type problems? Of course, we have ensured that EN is 0. So what happens, and this has been verified by statisticians, so we're not going into the details, but of course that exists here, and it takes the form of something like this, and this is of the order D over N, which is really good. So in a linear model, this relationship holds, as I said, and this has been verified. So that's the first step of learning, which is really good. Okay, so this was the pseudo-inverse algorithm. If you think about it, it's just like a one-step process. Although it's a one-step process, but this step in itself, depending on the dimensions of the data that you're dealing with, it could be a really expensive one step, right? And generally speaking, this step can be of the order, and of course it is like it varies, could be of like, if this is like a d-dimensional data, it could be n times the number of data that you have, d squared plus d cube kind of a calculation here. So it can go up to the order of that. But yeah, this is an expensive step, but it is there. So that's that. Okay, a little bit like before we end this lecture, a little bit about classification. So if you remember the pocket algorithm, right, for classification, and in the pocket algorithm, we said that minimizing EN is a hard problem. In fact, it's a hard combinatorial problem, and we cannot achieve it, right? So this is like a hard problem to solve, very hard, in fact. We can use methods to improve, right? We can use some good starting point that can improve performance in pocket algorithm. And one such technique is that we can use pseudo algorithm. So how? Okay, in the pseudo inverse algorithm, we saw that like obtaining this WLIN is not that difficult. It's obtained easily, right? So in like if we have the classification problem, instead of like the y's that we have, the y's like as opposed to the regression problem, these y's would be only +1 and -1. That's the only difference, but still they will have some value, right? So we can still run this pseudo-inverse algorithm and produce my WLIN for a classification type problem, right? So now, like if this WLIN that we get for the classification problem transpose xi is almost equal to yi, which would be true because we have seen, and this is known, that this pseudo-inverse algorithm really performs well. So we can achieve this, right? So one way is that all we have to do is get the sign here for the classification problem and see the sign of like my yi's, because they have like +1 and -1. So that could be one way. The other way is because we know that regression weights perform usually they perform really well with a classification problem. This is known. So another idea could be to actually get this LIN for my classification for the classification problem, right? Let's get it. And once I have those, I know because of the performance of the pseudo-inverse algorithm, I know that this is a good starting point for my pocket algorithm. So then like make this your starting point. So make this your starting point, and it has been found that this is really efficient way of getting a good result out of the pocket algorithm. So this algorithm will be called regression for classification. If we do this, like the starting point is my pseudo-inverse, and then we kind of apply pocket algorithm, this is known as regression for classification algorithm. Right, so basically what we did is that we combined and we utilized the power that we get out of getting the gradient of E in equal to 0 and getting the optimal weights. But obviously, because it's a classification problem, although we can directly apply this, right? But that obviously would be a good starting point for the pocket algorithm because we have a good starting point. We know that we have achieved some sort of getting E in close to 0, if not exactly 0. Okay, and this has been known to work really well in practice, this regression for classification algorithm. So we have found not just like a way to solve the regression problem, but also how to improve our classification problem overall. So that was the linear model, one of the most powerful models that's known in machine learning. And with this, I would just like to end this lecture. Thank you so much.